This video is going to discuss the AP and PA, or parallel opposed field arrangement, and I'm going to use a homogeneous medium in the chest to describe kind of the dosimetric characteristics and what we have to watch for with our dose calculations, or MU calculations. What you're looking at is the Eclipse treatment planning system. I've scanned a rando phantom in, which is essentially an epoxy phantom that has simulated bony structures embedded in the epoxy. Rando comes in multiple slices, you can see here, that are basically sandwiched together and put into a backlock bag. You can tell in the sagittal view here that those slices aren't put as tight as they should have been. I have a calculation point at mid-plane, halfway between the anterior and the posterior surface. For this example, field 1 is set at 100 centimeter SSD from the anterior. Field 2 is set at 100 centimeter SSD from the posterior. And I have equal weighting between the two of them. My dose distribution is essentially a column of dose that I get from AP to PA. The advantage of AP-PA, or parallel opposed field arrangements, is that with this, the tumor is typically located midline, in mid-plane, center of the body. I get this hourglass shape, I'll describe that in just a second, that essentially covers all of my tumor. And as long as the patient is positioned longitudinally correct and laterally correct, vertically the SSDs can be off a few centimeters. In reality, the only thing that changes are the hot spots in the anterior and posterior sections of the body. The tumor coverage remains constant, so that's one of the advantages of parallel opposed beam arrangement. It's a little bit more forgiving on the therapist. It's easier to set up. They only have to take port films or one port film to set isocenter correctly, as opposed to if you had oblique fields, you'd have to take some sort of an anterior and a lateral orthogonal pair if you wanted to set all three dimensions. You can see that 100% of my dose prescription goes through the calculation point. That's how I normalize. My prescription happens to be 200 centigrade times 1 fraction normalized at a reference point, which is my calc point. If I take a dose profile from anterior to posterior, the red corresponds to field 1, the green corresponds to field 2, and the blue corresponds to the total. You can see red mimics a nice percent depth dose curve where we start right around the 20%. Dmax occurs right at Dmax for 6x, which is about 1.5 centimeters, and then we get a fall off region after that. From the posterior, we get a similar aspect where we have an entrance dose right around 20%. Dmax is 19.5. Remember, my 0 is in reference to the entrance at the AP. The phantom is 21 centimeters thick, so if I go 1.5 centimeters from the posterior of the phantom for Dmax on the PA, I'm at 19.5, and then I get a fall off after that. The blue is what helps us understand where the hourglass shape comes from in the isodose distribution. So the percent depth dose from field 1 and the percent depth dose from field 2 are added together, and they give us the total dose, which is blue. And we get Dmax, and then we get some fall off, but it doesn't fall off as much as one field because we have contribution from the opposing field. And then we come back and go Dmax on the other side. So this is why the hourglass shape occurs for an AP-PA, or a parallel opposed field arrangement. If I were to look at the DRR from this field, I have a 10 by 10 field size, my vertebral bodies and ribs. DRR is digitally reconstructed radiograph, so the bony images in this beam's eye view are reconstructed from the CT data. The PA is going to be the exact same field, just opposed. In this planning system, in the lower right-hand corner of the beam's eye view, I can see my gantry orientation with respect to the patient, And I can also see my beam's eye view orientation with respect to the patient, red meaning left. I go back to the AP, you can see nose is AP or anterior, red is left, and over here my gantry is rotated around the patient. So with an SSD setup, AP and PA were the primary methods of treating patients, because in order to set a 100 centimeter SSD, you either had to rotate the patient around the gantry, or when you rotate the gantry around the patient, you have to move the patient to reset your SSD. Because remember, now the majority of C-arm linear accelerators are isocentrically mounted, meaning they treat SAD. They have a constant source to axis distance. So if I were to set this patient up on our treatment machine at the AP SSD of 100, and then I were to rotate the gantry around to 180 to treat the PA, I have to raise the table up, in this case 21 centimeters, to set the proper posterior SSD of 100. Now if you contrast that to an SAD technique, I'm just going to align these fields to my calculation point. So this is an SAD technique. Now, my single point of rotation is around the calc point, which I could rename and call isocenter. Now I've recalculated, I still get the same hourglass shape. My dose distribution may have changed a little bit. You'll notice that my monitor units have changed. Okay, they've decreased because I've moved the point of normalization closer to the source of the machine. So now I'm at 100 centimeters SAD, so 100 centimeters to the source. Before I was 100 centimeters to the skin, and then I had to go an additional 10.5 centimeters to the calc point. So I was 110.5 centimeters from the source. So now I've moved 10.5 centimeters closer to the source. Inverse square would tell me that the monitor units have to decrease because I'm closer to the source and I have a higher intensity. My normalization is still the same, normalized to the calculation point. In this case, for the therapists, they can just set this isocenter point midline, mid-plane in the patient, and then they can rotate the gantry around 0 to 180. They don't have to move the patient at all. So an SAD setup is much more efficient at treating the patient. Because an SAD setup uses TMR, TPR, and TAR, which are independent of SAD, we don't have to worry about setting a specific SAD or SSD for the patient treatment. We don't have to worry about correcting for change in percent depth dose with the Maynard F factor, because TMR, TPR, and TAR are independent SSD. Now, in modern planning systems, there's a report that gets printed. And in this report, they list most of the geometric descriptions for the machine. If you look at field 1 anterior, I have 6x for my energy. If I go to the next page, here, my calc point, the fractional dose at that calc point is 50%. I have equally weighted beams, which means that I have 100 centigrade being delivered from this beam. The PSSD is my SSD to that point. I have my physical depth of the point within the patient, and then I have what's called the equivalent path length. My calculations are performed homogeneous, which means that I've overridden all the densities. I'm basically calculating on a water phantom. So the physical depth is the only thing that we're going to worry about. Field 2, 6x, the jaw sizes are listed here. my fractional dose of 100 centigrade, my SSD, which again, TMR, TPR are independent of SSD. I have my physical depth within the patient. The only thing that this particular planning system doesn't show is the blocked equivalent square needed for figuring out phantom scatter factors and then your corresponding blocked equivalent square field size for TMR or TAR. So that still has to be done manually on the beam's eye view. But most planning systems are going to have all of these data displayed in some sort of a format where you can enter these into your hand calc or whatever your second check third-party software is, you know, for example, RadCalc or MUcheck. So if I were to take a dose profile again on 100 centimeter SAD, it's going to look very similar. Field 1 is the red, field 2 is the green. I have a classic percent depth dose curve for an on-face field, and then I get a classic hourglass shape by the addition of the 2% depth dose lines. Now let's talk a little bit about normalization. Right now I'm normalized at 100% to the calculation point. You can see that the cyan colored line here is 95%. Turn that on a little thicker. Now let's say I have a target in here that the physician wants to cover with 100% of the dose. Well, right now, because of this hourglass shape and the fall off of the percent depth doses, I'm only getting 100% dose at the single calc point here, right? And as we move anterior posterior volumetrically, yeah, I'm getting covered by 100%, but not at midline. So if the physician wants 100% coverage, we need to normalize down to a different isodose line. And what that means is that 200 centigrade isn't going to be delivered to the calc point. 200 centigrade is going to be delivered to the 95% isodose line. If I put my doses in absolute dose right now, you can see up in the upper left that 200 centigrade is the thick red line. If I normalize to 95% coverage to the calc point, you can see what happens is that 200 centigrade now gets covered where the 95% line was, and 95% now moves to where the 90% was. So my isodose lines, you can see 95% is my thick red. Well, that represents 100% of the dose. So 200 centigrade is now going to the 95% isodose line. So now I'm covering the tumor. What did that do to my monitor units? 135, 136. If you remember before, I was around 128. So now my monitor units have increased respectively, and that makes sense because effectively what I'm doing is I have the same beam arrangement. All I'm doing is leaving the machine on for just a little bit longer to pump a little bit more radiation into the patient. By doing that, I'm delivering more dose for a set geometry. If I look at my calculation point now is not getting 200 centigrade. It's getting 210, 211 centigrade. If I look at the dose at a specific point, right at my prescription isodose line, which used to be the 95% line, now it's the 100, it's getting prescription dose. My calculation point is getting more than prescription dose. So again, if I change this back, I'm normalized at 100%. My 100% line comes in. You can see my 95% isodose line is back at 95%. If I look at the point doses here, I'm at 191. If I look at my calculation point, I'm right at prescription. So that's how normalization functions.